Welcome everybody to this session on PQC hardware. We will have three exciting presentations. The first one is titled Falcon Sign, an efficient and high throughput hardware architecture for Falcon signature generation. And the presentation will be given jointly by Yihong Xu and Yi Wu Zhang. The stage is yours.
Oh, thank you. Hello everyone. I'm Yihong Zhu. I and Yi Yang are both from Tsinghua University. We are both going to have today's presentation together. We are very glad to present our work. Falcon Sign, an efficient and high throughput hardware architecture for Falcon signature generation. Our presentation will cover 4 parts. I'm going to introduce the background of our work, challenges and motivation of high throughput Falcon hardware. Then Yi Yang will introduce key strategies in Falcon hardware implementations. And finally, he will show the results and the have comparison with the prior works. In 2016, NIST started the PQC standardization process. And after 3 round processes, by 2022, 4 games are selected as the final standards, including Cable, Delicium, Sphinx Plus, and Falcon. And it is to be noticed that Falcon is highlighted that it has advanced lattice structure and special security properties. In 2024, last year, the other 3 games, including Cable, Delicium, and Sphinx Plus, have been drafted for the final specifications. And interestingly, by now, Falcon is still waiting for the final drafts. It may due to its controversial floating point operations. On the other hand, Falcon's influence also persisted with the introduction of a Hawk, a fixed point variant inspired by Falcon's design. And the Hawk's game also remains in the second round additional digital signature standardization process by NIST. In sum, controversial Falcon's floating point operations needed to be assessed in hardware, and it also demands dedicated hardware acceleration for real-world efficiency and deployment. So the question is, why the Falcon is selected as the final standardized games? As we can see in the left table, Falcon, compared to the other games including MLDSA, Delicium, Falcon stands out remarkably against the other candidates in terms of its compact signature size. This is its most prominent advantage. The chart on the right further codifies the performance comparison, showing the significant difference in signature generation and verification speed. Falcon offers the smallest signature size, which is most crucial for low latency environments. It also has not that slow signature generation speed, which is a little slower than Delicium. Falcon requires less storage requirements of verification and achieves the fastest verification speed. In terms of application scenarios, first, Falcon is the only viable scheme for vehicle networks due to its ultra-compact signatures, as highlighted in true hybrid real-world environment requirements. Second, in server scenario, its performance closely matches the current pre-quantum algorithms, making it ideal for maintaining efficiency. For time-sensitive TLS applications, Falcon ranks top among all those games. However, these exceptional performance characteristics also need to be enhanced by the dedicated hardware, which is also lacking for the current research status. To fully leverage its good advantages in real-world applications, specialized hardware support is not just beneficial, it is essential. Next, I will introduce the motivation of our work and the challenges we aim to address. Implementing a Falcon signature generation accelerator faces three major challenges. First, its complex control pattern involves recursive operations, which cannot be addressed very well by the current solutions. Second, it requires handling multiple type dynamic size floating point operations. Third, the high latency discrete Gaussian sampling process is also the critical bottleneck for the Falcon's acceleration. The bottom table shows the current research status on Falcon hardware implementation, which is primarily based on hardware-software co-design. The platforms are RISC-V CPU or ARM CPU, alongside the high-level synthesize-based approaches. These solutions struggle to optimize all the critical processes in Falcon's game, including the compact control operations, floating point operations, and the Gaussian sampling process. The performance limitations across the existing works underscore Falcon's high computational complexity, as stated in the keynote speaker by Professor Ingrid. This clearly leads to the conclusion that an efficient and fully optimized hardware implementation for Falcon is still needed. Our core motivation is to develop an accelerator to address all these unique challenges. Our primary design objective is to present a high-performance hardware architecture tailored for high-throughput Falcon signature generation through the algorithm hardware co-design. The first challenge is the algorithm's complex control pattern in Falcon, which involves the recursive operations. To overcome this, we introduce a finite transition scheduling mechanism enhanced with dynamic task update strategy. Second, to accelerate the multiple type dynamic size floating point operations, which are computational demanding. We present a compact and configurable vectorized IP architecture that supports the vectorized IFFT, FFT, and split FFT, merge FFT scheduling operations. Third, to mitigate the problem of high latency discrete Gaussian sampling process, we designed a pipelined discrete Gaussian sampler module with optimized data flow in sampler to achieve the minimum latency. Together, these innovations motivate our accelerator to fully leverage Falcon's potential in practice. The third part is key strategies in implementing Falcon signature generation in hardware, and it will be introduced by Yu Yang.
Okay. This slide shows the overall architecture of the Falcon sign accelerator, and which address the three challenges we discussed earlier. The architecture has three main components. The first is a multi-bank RAM structure, and the second is the function unit, including the core LPU, and the assembly Z, and the hash point, the modules. And the third component is the central control unit, which coordinates all modules. All architecture has three key features for high-speed scenarios. The first is the memory-centric vectorized architecture. It accelerates each algorithm step and enable faster memory access and data exchange and processing. The second is we design a dynamic task update mechanism. Tasks encoded in 68-bit and driving all function units. And while dynamic task update mechanism was designed to process the complex recursive FF sampling, The third key feature is the streaming packing. We packing a portable unit to reduce the latency and the memory access. In this figure, we pack hash point module and integer to float point converter module to reduce the latency and the memory access. The first contribution of our work is the dynamic task update scheduling. Falcon's control flow is highly complex. Traditional finite machines has limitation in handling the recursive FF assembly, and the prior works which presented in the CHES 2020 using the pre-generated macro code can only address the cursor grain control, and for the recursive FF assembly, we are caused the huge program data overhead, and mostly we aim to support both dynamic and sentry, the two methods of signature generation. To address this, we proposed a dynamic task update strategy. All computations are task driving and fields like the polynomial dimensions and the source address and the destination address are dynamically updated based on the recursion tree, the position and the state. We designed 4 states is the right down and the left up, left down and right up, with the level aware scheduling to reduce. This reduced the memory consumptions from 36 kilobytes or 72 kilobytes to fixed 80 slices. While we can support both, extend to support both dynamic and sentry. Our second contribution is vectorized float point processing unit. We designed it to overcome the computational bottlenecks in Falcon signature generation. The pipeline FFT architecture is not suited for Falcon high-speed data flow and have poor reconfigurability. And the prior work, like vector FFT and NTT architecture, cannot lack scalability to more dimensions. So we design a vectorized FFT NTT architecture with highly reconfigurability and featuring 4 improvements. First, we extended FFT NTT to more dimensions. And the second is we design a vector the algorithm for split FFT and merge FFT to match the vector architecture. And the third, a butterfly unit that supports all Falcon floating point operations, such as add, sub, and floating point multiplication, and FFT, split merge, split FFT and merge FFT is designed. And for the FPU, we further optimize the area by removing the unnecessary floating point formats and hardwiring the constant of multiplications like this. Instead of using Xenix IPs, we reduce the DSP usage by 47%. The third contribution of our work is a low latency Gaussian sampler, targeting the Falcon's sampling bottleneck. Prior works have trade-offs. Host 2024 achieve high frequency but many cycles, and the date 2024 reduces cycles but runs at a low frequency. And our solutions optimize both latency and the throughput simultaneously. We optimize the sample Z in 4 ways. First, segmented processing with timing, with time hiding, by dividing the sample Z into 3 blocks based on the operation type and latency. And while we overlap the latency in the sampler loop to reduce the to improve the sampler performance. And the third is random number generation optimization. Since sample Z has irregular random number demands, we integrate a CHES-20 module for generation and dynamically monitor and refill the random number consumption to matching the sampling the performance. Finally, we optimize the inter-sample operation. When 2 consecutive sample Z calls using the same standard deviation, repeated operations can be merged. With all those optimization, our sampling achieves 13.1 speed up over the host 2024 and achieves 3.1 improvement over the whole date 2024 works. Next, I will present our results and comparisons. Our work demonstrates a significant advancement in Falcon hardware acceleration. This is a table of our results in the FPGA Think Ultra Scale Plus. Mostly we achieve the signature generation in FPGA is 0.86 milliseconds, and in the ASIC platform we achieve 0.19 milliseconds. Compared to the latest works, our area time product achieve 2.8 improvement to 22.2 improvement. And for the flip-flops ATP, we improve 1.5 speed up and to the 21.8 improvement. Well, in DSP ATP, we improve from 1.7 improvement and to this 4.2 speed up. Mostly for DRAM utilization efficiency, we improve from 3.5 improvement to this 21.5 speed up. And together, those results prove that our architecture effectively solves the Falcon's unique challenges and sets the new state-of-the-art benchmarks. Thanks for your attention. This is OEMS and the GitHub. Thanks.
Thanks for the presentation. We have time for a couple of questions.
Good morning. Thank you for the presentation. I have a question. You have the artifacts on your web page, so thank you for that, but you do not have all the code of all the implementation. You have only some parts like sampler Z or FPU, but there is no code for dynamic task update. So do you plan to publish all your code, or are there some limitations?
Oh, thanks for your question. You know, in our GitHub, we have open sourced all the core blocks of our design. So as for the whole implementation, we maybe open sourced later days.
Okay, and when?
So because we needed to apply for the Tsinghua University for requirement. So maybe at later days, we will open source all the code.
All the code within days. And
So because I cannot guarantee I cannot control the university guarantee. You know.
okay, thank you.
Thanks for the talk.
Sorry. For the first question, so maybe we can share the source code through the private way, not rather the public way. So we can discuss this question offline.
Thanks for the talk. I'm particularly interested in how you handle the recursive call for the sampling, because it is a recursive call. You may need a large memory to handle the stack, right? So how you do that?
Sorry, you mean the task update strategy?
The Gaussian sampling part, the tree structure. When you do the recursive call to sample it. Maybe in the first few slides, yeah, this one.
This one. So you mean the methods of the recursive operation?
Yeah, how do you handle the stack operation? Do you need keep a stack to keep the state?
About how to process the FFT sampling in this figure. First, I want to state that in each state, in this position, actually the operations are the same type, but their size is different. So our first things to do is to let hardware to know where the position it is. So we like this state to make to update its position. If you start the start point and you is the left down, and we will update the position of the level. So when you get a new position, we will to do the corresponding operation like this space FFT and or add floating point add and sub and or multiplication. And the most importantly, we will dynamically update the dimension. Actually, the polynomial dimension. We need to update this size, and the address. This address is source address and the destination address to let the operation know how to get the data to process and where to store. So we can do this. And this dynamically is designed to process this recursive sampling.
Thank you for your nice talk, and I have one question. In your paper, in conclusion, you mentioned that you're gonna make side channel resistance models. Can you tell me the details and what is the most leakage point or can be in your work?
Sorry for you just mentioned the sub channel resistance design.
Yeah, in your paper, as I see, you mentioned that further words can be like side channel.
We are just said we are resistant to the time-sensitive attack, not including the power attack or EM attack.
I want to ask, the result that you compare, is it with the full-blown system that come with the core? Can you understand my question?
Sorry.
Yeah, because comparing the accelerator itself with another result that comes with the RISC-V core is, I think, not same system. Can you get me?
You mean the
Yeah, the result that you compare again, is it only accelerator with accelerator comparison or accelerator with the full SoC comes with the core? No, the result part. the result. Can you,
Sorry, you mean the
No, no,
as
no,
the-
no.
as a
no, the result. Towards the end of your presentation. Yeah, I mean, you're comparing your result, right? But is it you comparing against accelerator only result by
Results,
other
okay.
people's or full-blown latency that comes with the RISC-V or cores
yeah, all the course.
or the cores? Okay.
Yeah.
Because in that somehow not unfair. If you're comparing the only accelerators with the system that comes with the core interaction.
All the time is calculated by the hardware module. It is not including the software part.
I'm sorry, but I think we are out of time for questions. You might have to take this offline. So please join me in thanking the speakers again. And the next presentation is titled Rudraksh, a compact and lightweight post-quantum key encapsulation mechanism. And the talk will be given by Suparno Kundu. Stage is yours.
Thank you for the introduction, and thank you for joining me for this talk, everyone. I'm Suparna Kundu. I'm from COSIC, Leuven, and this is a joint work together with Purdue University and IIT Kanpur. In this talk, I'll talk about our newly designed scheme, which is lightweight post-quantum key encapsulation mechanism, and we call it Rudraksh. I'll start with a very background, and then I'll discuss a little bit about our design strategies, and finally I'll show our result, also comparing with state-of-the-art implementations of post-quantum key encapsulation mechanisms. Finally, I'll conclude. And I'll start with our current post-quantum standardization efforts that was spent like almost a decade has been spent on doing the deciding and finalizing the standards. And NIST was one of the leading candidates to do that. They have selected Kyber and HQC as key encapsulation mechanism, one in last year and another HQC is in this year. And as a digital signatures, they have selected these three schemes. And most of the countries plan to follow these NIST standard algorithms, together with some extra candidates such as Classic Macaleese or FrodoChem for key encapsulation mechanism. However, there are several countries such as South Korea. They have organized their own PQC competition and selected two new schemes as key encapsulation mechanism, which are Entru and SMART-T, which are a little bit different than the NIST standards. And also recently China has announced that they will organize a new PQC competition, probably upcoming years. So this is the standardization effort that has been spent on PQC. However, most of the schemes for this, like in this competition, was designed for general purpose use cases. However, we have millions of devices which are resource constrained, and for them also we need cryptography. Some of such devices are like which connects to the gateway servers like not that frequently and also very irregularly. And for them, low power or area is more important compared to the latency or high throughput. However, we also have some cryptographic application which are normally applied on powerful devices, and they serve thousands or millions of such millions of IoT devices. And for them, latency or high throughput is more important compared to low area or power. So, but in this work, our focus was resource constrained devices and to provide security and especially post-quantum security to them. Now, although the NIST standard has been concluded for at least for the first round, still, historically, NIST has always accommodated new standards and new research results in their standards, which can be visible from ECC standards in FIPS 186 version, and that has been that was like started around 2000. However, they were keep modifying and including new curves to the standards, and that goes until like up to 2023. So they keep updating new, keep adding new results to their standardization. So they don't stop after after finishing one standard. So that was also a motivation for our work as well. So we shouldn't stop researching on designing new schemes, because thanks to NIST standardization, a lot of results came into places, from cryptanalysis to hardware implementation to side channel secure implementation, everything, right? So it was one of the motivations. Another was lightweight cryptography. Although there were like block ciphers such as AES or spawn ciphers such as SketchUp, which was standard for SHA-3, that was there for general purpose use cases, we still needed some lightweight ciphers, and that's why NIST organized a lightweight cryptographic standards competition, and they have selected ASCON cipher for resource constrained devices. So it is an example for lightweight cryptographic standards, so we thought that lightweight for PQC would also be very important in upcoming years. So it was another motivation for our work. And now I'll go to the goal of our work. Here, our plan was to design a learning with error-based key encapsulation mechanism. We didn't want to deviate too much from the standard. And also here, our goal was to design a low memory or energy, like a key encapsulation mechanism for low area or memory devices. And also, we wanted to provide chosen ciphertext attack security that is very much needed for several applications. So, and we didn't want to hamper the security part. And another important design decision, another important motivation of this work for us was we wanted to take hardware cost into account during design time. So we wanted to have, our design was very much motivated from hardware cost actually. So with this, whenever we try to go design a scheme, the most important thing is like the hard problem. Here, lattice-based, if we try to design a learning with error-based key encapsulation mechanism, our first choice would be like standard learning with error problem. And however, that has a very big matrix vector multiplication in that. And that is pretty expensive, this multiplication. And if we use this hard problem, then we would also have larger key sizes. And also, it also have stronger security proofs, and this problem is the oldest one in this variants. And one of the example that used this hard problem, that is Frodo. Frodo came actually. Now, on an improvement of learning with error-based instances, there is ring learning with error instance that replaced those matrix and vector multiplication to a polynomial multiplication, and that helps to make this implementation of any encryption scheme faster, and also it helps to achieve smaller key sizes. And one example that used this hard problem, that is New Hope. Now, after that, we have a trade-off between this learning with error and ring learning with error instances. That is module learning with error instance. There, we use polynomials and also matrices, matrix and vectors. However, here our polynomial size will be smaller, and also the matrix dimension or rank would be smaller as well. So it's kind of a trade-off. It has, yeah, people think that it has more security at least, as it has lesser structure than a ring LWE problem. However, whenever we try to find out the security of learning with errors or any variant of learning with error-based schemes, we consider this equation, where if the lattice, if the matrix dimension of LWE problem is n, and if the polynomial size of ring LWE problem is n, okay, and if the dimension of module LWE instance is L and the polynomial size is there n prime, then if this three, if in LWE and which is equal with in RLWE, which is equal with L into n prime MLWE, then the concrete security is considered equal. And one example that used MLWE is Kyber. Now we had our hard problems. With this, we also studied which schemes uses these hard problems. Here we have a graph. There we have LWR based schemes and LWE based schemes here. And in the right hand side we have the standard LWE or LWR based schemes, and we have in the left hand side we have, sorry, in the right hand side we have ring LWE or LWR based schemes. Now in between all these schemes, which are module 1, so we have a very large space that needs to be that we observe that it is not explored as much, especially for learning with error-based schemes. And in this work, we decided to explore that space. And also, I would like you to note one thing, that if we go from standard to ring direction, then the performance becomes better, as ring was introduced to give better performance. However, if we go from ring to standard dimension, then our memory requirement, or at least memory requirement, becomes smaller. So that it's kind of a trade-off we had to make when we try to make a design. Now we explored this specific area with polynomial size n equals 32, polynomial size n equals 64, and polynomial size n equals 128 for module learning with error-based key encapsulation mechanisms. And we found 3 sets of parameters for them. Together with, we had another key component when we try to design a key encapsulation mechanism or any post-quantum algorithm, basically encryption and also its digital signatures, let's say. Hash and extended output function. Those are auxiliary function. But as you have seen in previous talks as well, that although those are auxiliary function, those takes like huge amount of time and also memory. It almost 50%. And it after years of improvements in native operation of post-quantum schemes, it becomes the bottleneck. So in this talk, we have decided to use new or lightweight extended output function or hash function, that is ASCON. And what we observed that ASCON actually requires lesser area compared to KECHAK, which is normally used as hash or XOF function in post-quantum schemes, as it is the SHA-3 standard. And also we observed that ASCON provides better throughput per area result as well. So to do a lightweight design, it is very beneficial. So we have taken this specific cipher as hash and XOF as our first step to design a lightweight scheme. And after that, after deciding those parameters and this hash function, we estimated the cost of our schemes. That includes these 3 schemes, which is KM-Poly 32, KM-Poly 64, and KM-Poly 128, together with Kyber and New Hope. Okay, And here I didn't include Frodo. It goes beyond this curve. That's why I didn't include that one. But as you can see, even if we search module space, this poly 64 took least amount of memory in our calculation, in our given hardware design, which we concluded that is the best one, at least in our opinion. And that's why we took this scheme, this key encapsulation mechanism with this hard problem, and with this polynomial equals 64 as our lightweight key encapsulation mechanism, and we call it Rudraksh. After choosing this scheme, we went to implement it efficiently as possible in hardware. And to do that, one very important thing is we have to do a careful hardware scheduling, right? That's very important to reduce extra memory requirements and also to reduce stall cycles as much as possible. And here I have given an example of public key encryption, key generation algorithm specifically, and here we use this scheduling for this algorithm. Here, as you can see, we have ASCON and Butterfly, these two modules. ASCON is used to sample the polynomials of the matrix A. Sorry, polynomial of matrix this A, and also for these secrets. And we use Butterfly to do number theoretic transformation and pointwise multiplication, and also inverse number theoretic transformation when we need it. So we just use these two modules basically, and careful scheduling. After that, as we have chosen 64 size polynomial, we needed, and we also chose actually learning with error problem because we wanted to do number theoretic transformation on them, as it is very memory efficient if we can do that. And here we have chosen 64-point entity, and our prime is our prime is a 13-bit prime, and with that prime we can do actually complete entity. So we have opted for complete entity, and we also search for several modular reductions because it is also a core component in the butterfly operation, and we search for several modular reduction algorithm. And what we observed that shift and add based modular reduction that takes least amount of area with our implementation. So we have opted for this modular reduction. And after that, after all these improvements or all these design decisions, and after taking them and after implementing them to as optimally as possible on hardware, we observe that our Rudraksh takes almost provides 3x area improvement compared to the area optimized implementation of Kyber. Here I have just given one area optimized implementation of Kyber's area result and our Rudraksh results. And when we try to compare them for time area product, then we observe that it provides almost 2x improvements compared to the compact implementation of Kyber. Please note that the previous Kyber implementation that we cited, that is area optimized, and this one is time and area product optimized. So our Rudraksh doesn't only provide area efficiency, it also provides time area product efficiency. And with this, it takes to me the key takeaway of this talk. That is, here our hypothesis was there were several devices for them, low power or low area is much more important compared to throughput or latency. And it was an attempt to design a lightweight key encapsulation mechanism that can provide chosen ciphertext attack security. So we didn't want to reduce the security assumptions. And and it is the fast hardware-oriented post-quantum key encapsulation design. And here we have introduced a new module lattice for learning with error-based hard problem. And we also, we have a kind of observation that this lattice can be made with this structure, you can actually have higher speed if we can parallelize all this matrix polynomial multiplication. But in that case, we would require more area. But it is a very flexible design. So it's just a point I wanted to note in the end of my talk. And another important thing is it was the first or second scheme that used ASCON as the hash or XOF function, and we have implemented our scheme Rudraksh on hardware as efficiently as possible, and we saw that it provides almost 1/3, almost 3 times improvements in compared to Sabre area optimized implementation of Kyber. Yeah, thank you for your attention. Now I'm happy to take any questions if you have.
Thanks for the nice presentation. We have time for a few questions. Maybe I'll make the start. Do you plan to submit this to the Chinese standardization competition?
We are thinking to. Let's see how it goes.
But the hope is that NIST at some point does a call for lightweight CAMs in 5 to 10 years or something.
Probably, or maybe we may have a need in several applications that we may need lightweight post-quantum crypto, and there we may need to include it, even though it might not be the standard. If it is highly evaluated, then I think it's possible to take into account, but I'm not saying without evaluating them, but I think there are several applications, and for them, probably it's really needed. And probably there are, still several standardization are happening and will happen. Probably not the NIST one, but other standardization body, they may organize new standardization for several different applications, probably not the primitive, but as an application of primitive. So there we can try to submit it.
Yeah, I strongly agree that there is a need for more implementation-friendly CAMs. So it's a great direction. I've one more question. There's one up there.
Hello. Great talk and very nice ideas. I'm just curious, from the various performance improvements that you showed, what part stems from the choice of parameters for the hard lattice problem, and what part comes from the ASCON choice for the hash function and XOF?
Yeah. We have that in our paper, it is, I tried to make the talk as compact as possible. So it was kind of 50-50 improvement we got from ASCON and also from our design choices. But for more details, I would suggest to please look into our paper. There we have more details, how much improvement we really got from ASCON and how much from all other design choices. Because if you notice, we have two components actually, right? One is the butterfly and another is ASCON. So, and even though the improvements we get from ASCON, that's also to have that improvement, we had to modify our design so that we can get those improvements, So it's kind of dependent, I'd say.
Okay, and have you evaluated, just for the sake of trying, have you evaluated switching Kitchak for ASCON and Kyber to see how it would impact the performance as well? Or was it not? Was it out of scope?
I didn't do that, but as I mentioned that we were probably the first or second one that who used ASCON in their implementation. We actually, when we are submitting this paper to conferences, then we noticed that there is a paper they very recently included ASCON to Kyber implementation. Although ASCON does provide improvements in Kyber, but it is not as much as here. But
Right.
we didn't find any hardware implementation for that, and we didn't want to, compare Cortex-M4 implementation. I don't think it's fair, so we didn't do that. But yeah, we can do that. But it wouldn't give you, like a very core, like I would say, a very good idea. Like if we can optimally replace ASCON in Kuiper, how it would affect. Because you have to take into account this thing, right? This is very important. You have to make it as parallelizable and as like scheduling should be very fine-tuned to get to have all these improvements, at least for hardware. But for Cortex-M4, it's a little bit easier, I'd say.
Yeah, of course. And one last question is on the graph where you showed the difference in memory requirements between your scheme and, for example, Kyber and New Hope. I'm curious if this includes because the requirement that is showed, is it based on the reference implementation or is it based on, so I'm curious what implementation it's referring to. And on the contrary, this graph for CAM Poly 64 and Poly 128, is it based on an optimized version or is it just a straightforward approach? And that will be all.
It is based on an optimized version, which we estimated. Like least amount of memory, least amount of elements we would have to store when we implement it. And we have used same architecture for all of these schemes so that we can compare them in the same environment to have a fair comparison,
Okay, so Kyber and New Hope are the reference versions?
No, it's not the reference implementation.
Okay.
It's with our estimation with least amount of storage we would need.
All right, thank you very much.
Yeah, we have more details in the papers.
Thank you.
Thank you for your questions.
Okay, please let's thank the speaker again.
Thank you.
And now the final talk of this session will be titled H-Raccoon, a high-performance configurable SCA resilient Raccoon hardware accelerator. And the talk will be given by Sijing Ni. Stage is yours.
Thanks for introduce. Hello everyone, my name is Zijing Ni and I'm from the Queen's University, Belfast, UK. And the title of my presentation is Raccoon, a high-performance configurable SCA resilient Raccoon hardware accelerator. And this work is collaborated with Nanjing University of Aeronautics and Astronautics, China. So, first of all, I think most of us should know that the high speed of the quantum computers and some quantum computers-based algorithms pose a serious threat to existing cryptographies like ECC, ISA. So from 2016, NIST initiated the PQC standardization. Until now, they have already 4 rounds and 5 different PQC schemes have been selected and will be standardization in the future. And most of them are lattice-based cryptographies. And also NIST initiate the additional digital signature schemes. And also for round 1, there are 41 algorithms, including Raccoon. And the round 2, there are only 14 algorithms. Raccoon has been selected in round 1, but unfortunately it has been selected in round 2. But they have still have some high research values because it's built-in masking lattice-based cryptographies. So the speed and error under the masking is better than other standardization PQC plus masking solutions, and also can touch it to other NIST processing. So so there are 2 fingers to show the advantage of the Raccoon compared with the standards. So the finger 1 shows under the software implementations, the Raccoon with the security level 3 and has 13 shares, and the operation time is just similar with the unmasking Falcon. And the right finger shows, the finger 2 shows the software and hardware core designs results. So the Rukun has compared with the Dinithium under the same security levels and same shares, and the recycle counts is just 3 times reduction compared with the Dinithium. But they still have some challenges. So till now, all of the implementation of the Rukun are based on the software and the software hardware co-designs. So there are like the evaluation of the high performance on the hardware devices, and also like the security evaluation on the poor hardware devices. So what is the Rukun? So Rukun has the similar framework with the Dinithium, but there are 3 key differences. The first is the sampling process for security key. Rukun replaces the rejection sampling to the sums of the uniforms. The second is the rejection loops in the Dinithium is no need in Rukun. And the third is in the high order masking, the overhead of Rukun is reduced. So what is the sums of the uniforms? And first of all, for each polynomial samplings, the random number is different, which is different with the Kyber and Dinithium. And the second is for each sampling loops, D shares are filled independently. For example, if we choose D equal to 2, so they have 2 shares, share 1 and share 2. So for the first sampling, we just filled into the share 1, and the second polynomial we filled to share 2, and then refeature these 2 shares and repeat this process for 4 times, then we got a polynomial with the share. And they also prove that this process is NIU and replace the traditional NI, so it's even it remains secure even without masking. So the overall algorithm follow of the Rukun is just a brief talk about this. So for any side in the K generation, first to got a K, and then sampling the matrix A, and then sampling the masking security key, Leucin polynomial, and make the polynomial multiplication, and then decode it, polyshift it. And in the Steiner siders, so first 3 steps were just similar with the K generation, but the bitwise of the security key is large, and then got the challenge poly and challenge hash, and then the Z and H, and package them and send it to Bob. So in Bob's side, first check the boundaries of the signature, and then got the challenge polynomial, challenge hash, and check the challenge hash he generated with the signature sent by Alice. So for parameters, the modules of the Rukun is not a primer, it's the product of 2 small primers, and the bitwise were up to 14 bits, and polynomial degree is up to 512, which is doubled compared with the Kyber and Dinithium, and they definitely have 3 security levels, security level 2, 3, and 5, and controlled by K and L. We show a part of the parameters in table 1, 3 security levels, and in each security levels has D equal to 1 and D equal to 2, which is used in our proposed architectures. So the overall architecture just shown in figure 3. This is the first poor hardware design of the Rukun, and it has 2 siders, the Steiner siders and the very first siders designs. All these 2 siders have some similar components, like the controller, SHA-3, sampling, memory, polynomial operations, random norm generation, fridge, and bound check models. First, for the SHA-3 models, they only have 1 single KHR core, and for the sampling models, have 4 samplers, but they actually have 3 of them because there are 2 types of sampling U for security key, and also has the first stage of the challenge polynomial samplings. The polynomial operation modules built from entity and polyshift models. The memory models have 4 small fibers to like the buffer to storage, template storage, the polynomial of the matrix A, and also the BROMs. The random number generation models is only in Steiner side because in the very first side it doesn't require masking, and also they will have fewer BROMs. And for reflection models, have 2 adders, and the subtribute models will be shared to use. So first of all, we should to define the basis of the overall architecture, the modulus we use. So I have 2 choices. The first is to use a large queue. So the bitwise will be 14 bits. So it's very hard to use the few DSP to construct that, and a lot of DSP will reduce the overall frequency, and the cost is a product of the primers. The reduction is difficult to design. So we choose to use RNS systems with two small primers. So the multiplication bits will reduce to 25, but it's also execute the capability of the one DSP. So we use the finger in the right side to split it. And then the primer structure is just like the Kyber and thin film, so it's very easy to design the modular reduction models. So we propose three different reduction models. The first is arithmetic-based reduction. So we use the formula simplification to reduce the bitwise of the product C. The second way is the Barrett-based reduction, so we use the shifter and adder to replace the multiplication in the Barrett algorithms. The last one is a K-based reduction. We use the lookup table modes to reduce the MSV of the product C. And to compare with the three modes we propose, we found that the K-based mode has less resources consumption, but they have one problem because in K-based modes and the last step we need to process data reconstruction. That means to remove the factor of K, but in the signature stage, the bitwise of the security key were large, so we need more lookup tables, and they will reduce the overall frequency. So we use a Barrett-based reduction modes in the overall architecture. And for the polynomial operations, we use the FIFO-based entity with two butterfly units, and each will contains entity, identity, and PWM, and also the polynomial adders operations. And also all the components in the entity, like the multiplications, adders, subtracts, and FIFOs, will support these two primers. And there are three small FIFOs in the entity. And the next is the polynomial shift. It's very easy to do that in the logical, but because the shift number is larger than the bitwise of the small primers, so we couldn't do just a shift in the RS systems. So we first convert to the logical and then shift it. So in this case, we need 17 4-bit reduction for the logical. But if we will use the logical for the overall architecture, the bitwise of reduction will increase to 19.8. And this reduction models is implementation by the LET-based approach. So the figure 5 shows the configurable sampling models include the sampling Q for matrix A, and sampling U for security key, and the C poly for challenge polynomial. And these models will got input from the hash models with a bitwise of the 16.4, and use a different instruction to select different data paths. And the sampling U models will support two types of the security sampling, and also have a reduction models here to make sure that all of the output of the sampling models are in the RNS systems. And figure 6 shows the second step of the challenge polynomial generation. So because the overall architecture in RNS systems, so these models will connect with two BROMs, one BROM to storage the data in the Q1 and another data in the Q2. They have 3 steps. So first of all, use the challenge hash to determine the address of the these two BROM from the port A, and then the second step to use the LSB of the challenge hash and the data in the address, and to determine the address and the data we want to write in the BROM. And the last step used another port, the port B of the BROM, to write the data. But they have a small problem in the algorithm to the signer stages, because they will use challenge polynomial 2 times. The first time is just to multiply with the security key, and the second time is first the value first to shift with VT and then multiply with T. So we couldn't do that directly in the RSA systems, so we just to do the pre-computing and storage 2 of the C-poly values. And for the random number generation models, we use LFSR to generate the basic random numbers, but it could be very easy to replace as a more complex one. So the next is memory and access pattern. So the proposed design has three memory parts. The first is the general computing memory area, the BROM A. The second is the secret key memory area, the BROM SK and the BROM R. The last one is the public key memory area, the BROM TS. So the secret key memory area have 4 BROMs with the same size, and 2 of them for secret key and for SK, and 2 of them for R. The public key memory area used to store the data from the decoder and the polyshift models, so it only have 1 BROM with the small size. And the last one is general computing memory areas also have 2 BROMs with the bitwise of the 15th. So it could, so this bitwise could make the BROM to hybrid storage data from Q1 and Q2. We also define 4 storage models like the refresh, sampling U, PWM, INTT to make sure that we could the 2 ports of the BROM is enough for us to use. So for scheduling, the first is processing strategies. I have 2 strategies we could use. The first is column-wise processing. So in this case, we could generate the secret key with just on the fly and multiple with matrix A. But the problem is the results of the polynomial multiplication here couldn't be decoded. So because it's unsafety here, so we need a large number of memory to storage the results of PM. The second way is row-based processing. So in this way, we should to generate all of the secret key with the shells and then storage all of them, and then make a multiplication with the matrix A. In this case, we could decode the results of PM and polyshift this and storage in the BROM. For the segmentation and loop-based scheduling, the proposed architecture use a single computation just to make the scheduling in a single computation unit. That means just to scheduling in once time entity and once time SHA-3, and use different parameters like D, L, rep K to determine the loop times of each operations. So the proposed design can support 6 different parameters. So and the last, for the matrix A in the signer functions, because it's very large, so we couldn't to storage this. So we will re-sampling this in the second stage of the signer functions. This is different from the software designs. So we implementation our proposed design in the Architect 7 and compare with the proposed Rukun designs. For the software designs, the proposed design has 1.4 to 2.1 times speed up. For software and hardware core designs, we have 20 to 42 times speed up. And compare with the standards, like under the same security levels, same masking degrees, compare with the DIN we can 1.5 times speed up. And compare with the SLH DSA, we have 2 to 5 times speed up. And for area, the proposed design just have the comparable area consumption compared with the software and the hardware Rukun core designs, and compare with the standardization, the proposed design even less, the area even less than the no masking lightweight DIN designs. So we also use TVLA to test the proposed design. For setup, we use chip-witches per devices, and frequency we set to 5, and they'll have a large number of sampling points. So the threshold extended to 5.5, and n equal to 20,000. So just compare with 2 fingers, we found that all the operations involved with secret key, like the NTT, PWM, and calculation Z, has no leakage under the masking. So in conclusion, for this paper, we proposed the first Power hardware accelerator for Rukun, and the proposed Rukun architecture will support 6 different parameters. And the results show that the proposed architecture has a disadvantage in operation times compared with proposed Rukun design and also standards PQC designs. And the area of the proposed design is just comparable to the lightweight DIN in implementations. And finally, we use the effectiveness of the masking is verified using TVLA modes. So thanks for this is my presentation, and the code of this paper, code of this architecture has published in GitHub. Thanks again.
Thanks for the presentation. We have time for a few questions. Could you go back to the comparison with Dilithium?
Yeah, yeah.
Yeah, this one. So you say your speed up is 1.5 at like 2 shares, so first order masking.
Yeah.
Now the expectation would be that if you increase the masking order, the speed up would be significantly larger, right?
Yeah.
Okay. But you do not have concrete numbers for like 3 or 4 shares?
Yeah, for this architecture, we only implementation the no masking and first order masking. And for maybe high order masking will be the future work for this.
Okay. Any questions from the audience? Okay, then the talk was very clear. Let's thank the speaker again. And now we go to lunch.